Hello, my name is Carl Denise, and today I'll be explaining radioactive decay, which is an important concept to understand if you're interested in exploring half-lives, transmutation reactions, or even just the causes of radiation. So let's start with a quick recap of why decay occurs. So in any nucleus, and in this case I use an alpha particle as an example just to keep it simple, any nucleus is made of positive protons and neutral neutrons. The protons here repel each other due to their similar charges, but the nucleus is held together by a short-range attractive force that exists between the nucleons, called the strong or nuclear force. However, heavier nuclei, like uranium, have more protons, in this case 92, and experience more long-range Coulomb repulsion and require even more of the short-range strong force in the form of more neutrons to overcome this. This means that the neutron-to-proton ratio increases with heavier nuclei as they attempt to keep the nucleus stable. However, when the atomic number is greater than 83, the neutrons can no longer compensate for the repulsion between the protons, and they are unstable. This is why the actinides, including uranium and thorium, are unstable. So nuclear or radioactive decay occurs when these unstable nuclei break apart into smaller pieces by emitting radiation through photons, particles, or both, which we'll cover later, until the decay product reaches a stable neutron-to-proton ratio and has achieved stability. So there are three main types of radiation or decay, known as alpha, and here's a symbol here, beta, and gamma. So alpha decay occurs when a nucleus emits an alpha particle, or a helium nucleus, that has two protons and two neutrons. As seen in the example, the daughter nucleus is lighter and has a lower mass than the parent nucleus. Beta decay occurs through the emission of a beta particle, which is an electron, and this is done by breaking down a neutron into a proton, which will stay in the nucleus, and an electron, which will be released. So beta decay does not dramatically impact the mass number of the parent nucleus, as you can see here, but rather changes the ratio of neutrons to protons. Unlike alpha or beta decay, gamma decay does not involve changing the atomic or mass number of the parent nucleus, but rather decreasing the energy level of a nucleus that was left in an excited state. So here, the only reasons that the atomic and mass numbers have changed is because gamma radiation often occurs alongside other forms of radiation or decay, and here it's alpha. So the gamma rays, or the high-energy photons that have no mass, are ejected from the nucleus, causing the nucleus to decrease in energy level.